All right, in this video we're going to talk about Euler's method, and Euler went about it with a lot more brute force than with slope fields. And what Euler's method is good for is finding or estimating a specific value on a function. So for example, we'll use the same differential equation from the slope field. Use Euler's method with 5 steps of equal value to estimate f of 1 if we know that f of 0 is equal to 2. That was the initial condition that was given above. So our starting point is 0, 2. And we want to take 5 steps to get to f of 1. So that means we want to go from 0 to 0 0.2 to 0 0.4. I should leave a little more space. You'll see why. To 0 0.6. to 0 0.8, and finally when we get to 1, that's what we're looking for. So this will be the answer that we're curious about. That was really too big. So this is going to help us. We're going to literally graph one single point at a time. Now this is an estimate because we're using a slope to figure out how much y is changing. Because with the slope that you're used to from whenever you learned slope for the first time, we know that a slope of, let's just say 2, means that this is the change in y every time x changes by 1. That's what a slope is telling us. How much does y change every time x changes by 1? Well, in this case, x isn't going to change by 1. We're changing x by a value of 0 0.2. So, specific example. So we have a starting point of 0, 2, and I know that dy over dx is equal to 2xy. So what I really want to find out, because I know dx, or the change in x, is 0 0.2. So what I really need to find out is, what is dy? How much is y changing at each of these points? And we know that the slope is not the same at every point because this is not a linear function. So we need to figure out at every single point on this graph, how much is y going to change by? So if I move the dx over, that's going to tell me what I need to know. So let's start calculating. Let's find the first change in y. So at 0, 2, what is the slope at that point? Or in other words, how is y changing? So I can say that dy is equal to 2 times the x value times the y value times the change in x. So in this case, I can see that if I multiply 2 times 0 times 2 times 0 0.2, I know that at this moment in time, y is not changing at all, because it's 0 times all of that. There was no change in y from that at that first point. So my new point then is the x value is going to increase by 0.2 because that's the change in x. The y value is not increasing at all, so that y value stays at 2. Okay, so that's now the new point I'm going to start with, is 0 0.2, 2. Now I'm going to find dy. dy is 2 times x times y times dx. How much is x changing by? 2 times 2 is 4. 4 times 0.2 is 0.8. 0.8 times 0.2 is 0 0.16. Okay, so now my new point, I know that x is changing by 0.2 every time, and I know now that y changed by 0 0.16, so that means my y value went up by 0 0.16, so that's the new y value. Okay, now I'm going to get to the point where this is going to start to get a little bit longer, but what I need you to do at this moment, I need you to pause this, and I want you to go start doing these calculations on your own, and then come back. Okay, welcome back. Let's finish this off. So let's find the next change in y. dy is 2 times x times y times dx, and I've pulled out my calculator because I I'm not going to do that in my head, so 0.8 times 2.16 times 0.2 is 0.3456. Do not cut off your decimals. That was kind of cool that it's 3456. I hope you found that as fun as me. Don't cut off your decimals because we're going to have to keep carrying these over. And so the more you round now, the more off you're going to be on your answer. So wait until the very end to round things off. So the next point is at 0.6 comma 0.3456 plus what it was before, because this is just the change in x, remember? So this is 2.5056. Yeah, this was Euler. Euler did this literally 1 point at a time. Got a little tedious. All right, next dy is 2 times x times y times dx. Calculator, so 2.5056 times 0.2 times 2 times 0.6 is something very long. 0.601344. Okay, so now we're at 0.8, we're almost there, and add 2.5056 to that, 3.106944. So close. One more time. Okay, so dy then is 2 times 0.8 times 3.106944 times 0.2. That's getting long, but we've got this. 0.99422, I'll just write it, 9942208. So if I add that on to 3.106944, then we can estimate that f of 1 is approximately 4.1012, just to go out a ways. It was actually 4.1011668. That's a lot, but let's see how close we were. Because we had the original function. The function was 2e to the x squared. So let's plug 1 into that 2e to the x squared and see what we get. So 2, I'm doing this in my calculator, I hope you are as well, times e to the first, oops, hold on. So if I do 2 times e to the first power, sorry, I was pushing the wrong thing in my calculator. I'm using my phone. I got approximately 5.4366. Not the best. If we would have used smaller increments for x and made more of them, then we would have gotten closer. So this is not a great estimate, especially because this was an exponential function. But the more of them we would have done, the more accurate we would have been. So not a great way to do it, but still kind of gives you something close. All right, that's Euler's method. I know. Don't ask me. All right, talk to you later.